From here that the impedance to be matched by using quarter wave transformer is not a real impedance. Let us say a load impedance of 75 minus j35 ohms is to be matched to 50 ohms using quarter wave transformer. Design the matching setup. Now, if you recall, the quarter wave transformer basically can match two resistive impedances. Since our characteristic impedance is real, any real impedance can be matched to the characteristic impedance. However, the impedance which is given to us is a complex impedance, which is 75 minus j35 ohms. So, by using a section of a transmission line, first we must transform this impedance to a real value. At that location, we insert a quarter wave transformer and we get a match. So, the setup essentially would be that this is the unknown impedance, which is 75 minus j35 ohms. I introduce a section of a line of the same characteristic impedance. Let us say this is Z0 is 50 ohms. So, this line also is of characteristic impedance 50 ohms. Then the impedance transform seen at this location should be real. So, at this location I can introduce a quarter wave transformer, I will get a match. So, now two things are to be found out in this problem. First is what should be this length and what should be the characteristic impedance of this quarter wave transformer. The length of the quarter wave transformer is lambda by 4. For finding out the impedance at this location, which will be real, and the length, we again make use of the Smith chart. So, first thing what we do, we take the Smith chart, mark the unknown impedance which is to be matched to 50 ohms. So, first we normalize this impedance of 75 minus j35 ohms, mark this point on the Smith chart. Draw a constant VSWR circle passing through this impedance. So, this circle is the constant VSWR circle corresponding to the load impedance 75 minus j35. Now, as we move on this constant VSWR circle towards the generator, that means on the clockwise direction, if I move by a distance corresponding to AP, the impedance at this location seen will be real and it is the minimum resistance which we will see on the line. If I move by a distance corresponding to AQ in the clockwise direction, then I will reach to a location of voltage maximum and then the resistance seen at that location will be R max. So, there are two possibilities: either I insert a length of transmission line between the load and the quarter wave transformer by this, and then the impedance to be matched will correspond to this value, or I can take a distance corresponding to this and then the impedance to be matched will correspond to R max value. So, there are two solutions to these problems. Firstly, if I move by a distance AP, and how I measure a distance, I take a radius vector, go to the circle here, here the lengths are marked on the outermost circle of the Smith chart. So, it starts from 0, then it goes all the way up to 0.25 and then goes up to 0.5. So, here the circumference is calibrated in terms of lambda. So, I can take a radius vector, read off this value, this is 0.306. If I move up to a point P which corresponds to 0.5 lambda, difference of these two will tell me the length of the line which is to be introduced between the load and the quarter wave transformer. So, one possible solution is that if I take this length, then that length will be 0.194 lambda and the impedance to be matched will be R min, and that will be the 50 ohms multiplied by the normalized value here, which is 0.5. So, now I get the impedance to be matched will be 25 ohms. If I insert a length of a line between the load and the transformer of 0.194 lambda. Other possibility, if I go from A to Q, then the distance will be AQ will be 0.194, which is this distance, plus lambda by 4, 0.25. So, that distance will be 0.444 lambda. So, if I introduce a quarter wave transformer at a distance of 0.444 lambda from the load, then the impedance to be matched will be R max, and that will be 50 into normalized value 2 corresponding to this point Q. So, if I take this as L in this case, then the impedance to be matched will be 25 ohms. So, the characteristic impedance of the quarter wave transformer will be geometric mean of the characteristic impedance and the impedance to be matched, which is 25 ohms. So, the characteristic impedance of the quarter wave transformer will be 35.35 ohms. On the other hand, if I take L as 0.444 lambda, then the resistance to be matched will be 100 ohms, and then the characteristic impedance of the quarter wave transformer would be geometric mean of 50 and 100, and that will be 70.7 ohms. So, in this problem we see how to match a complex impedance to the characteristic impedance by using section of a transmission line and the quarter wave transformer.